there's going to be a couple of announcements before Jay's last lecture. He is very sad, but it's okay. So please, I don't know your name, I'm sorry.
Gabriel.
Gabriel is going to make an announcement. Please.
So I have a little announcement. So the students of IFT, they do a little colloquium. We call colloquinho. It's literally a little colloquium. It's a student colloquium where we talk about something of our research, etc. And it's a professor-free, a safe space for us to make maybe dumb questions, not often, but no professors allowed. And you're all invited. It's going to be 5 p.m. And then afterwards, after the colloquium, we have some gathering nearby, and you're also all invited. I think those in the group have read the message, and that's it. That's the announcement. Hope you see you. Oh, it's not it's not mandatory. Like it's nothing to do with. It's cool. Oh yeah, sorry. So it's gonna be one of you actually. It's gonna be Pedro Bittar. He'll be talking about asymmetric twin dark matter. So here. Here, yeah, here, 5 here. If you want to be here, you may go home, I don't know.
Thank you, Gabriel. Okay, so...
yes, and then I've had a number of people ask questions about the student talks. So today at 4 p.m., there's nothing. You can all take a nap. The student talks are going to be Monday at 4 p.m., after the end of the 3 lectures that we have next week. And you should send me a PDF of your slides by Monday at noon, say, or Monday during the lunch period, so I can gather them all together. And then as many talks as we have, I will fit into the hour, so your time may change if there's more people that volunteer. Okay?
So it's a time-changing talk. Okay, so now, please, Jay, take it away for the last lecture.
Is pick up where we left off yesterday, which was we were interested, remember, in taking this classical picture, which we saw helps us solve some of these problems associated with cosmology, the horizon problem, the flatness problem, the heavy relic problem. And we want to see what happens when we add quantum mechanics to the mix, because we know the world is quantum, so we better see what predictions we get from that theory once we take it seriously enough that we want to quantize the theory and see what happens. And so we started off with this classical picture with a scalar field rolling down a relatively flat potential. And what we now want to do is think about the possibility of there being quantum fluctuations, delta phi, of this field rolling down this potential, okay? And these are the things that give rise to those perturbations that then seed later on the fluctuations that we see in the CMB and that give rise to structure at late times. This is a relatively complicated problem at first glance, since it involves sort of 2 sectors at the same time, a scalar field interacting with Einstein gravity. So before we actually look at this picture, we're going to look at a more simple picture where there is nothing but a free massless scalar field living in a de Sitter background. Okay, and we started to look at this a little bit. We started with the action, and I'm just going to go very quickly. We already did this. Minus 1/2 d4x d phi squared. Okay, and that's it. The exception of a root g. We saw that we could reparameterize this action and absorb the time dependence in the background into the scalar field, which allowed us to write down a theory of a canonically normalized scalar, but with a mass term that depended on time. So we defined V is equal to A. I was using little verify here. A verify. And in this case, the action simplified to d for x v dot squared minus di v squared, the gradient term, and then the mass term a double dot over a v squared. And then the equation of motion is for a given wave number, k is vk double dot plus k squared minus, and let's plug in for a double dot over a. Given the fact that we are in de Sitter space, it is minus 2 over tau squared, and then times vk is equal to 0. Okay, and remember for de Sitter, we have a is minus 1 over h times tau. Okay, and as we said last time, there's something interesting about this equation that we note, and that is that at early enough times, when tau goes to minus infinity, then for any particular mode number k, at early enough times, this is going to look just like the standard wave equation in flat space. Again, due to the fact that if the wave number is high, then that mode doesn't know about the de Sitter curvature. Okay? Okay, so that's about where we were. And now what we want to do is follow the usual procedure for quantizing the modes that satisfy this equation of motion. And we'll just do it the canonical way, where we have our canonical coordinate q is v, and our conjugate momentum p is pi is dl by dv dot. And then what we want to do is we want to promote these coordinates and their conjugate momenta to operators. So we just add hats. And we'll work in the Heisenberg picture where the operators take into account the time dependence. Okay, so the states are stationary and the operators are time dependent. Okay, and now if we want this to be quantum mechanical, then there has to be a commutation, a specific commutation relation, an equal time commutation relation between these operators, and that is that v hat at tau and x with the conjugate momentum operator pi at equal time and x prime is I times the delta function x minus x prime. Okay, so these are the equal time commutator relations for the coordinates and their conjugate momenta. And you can Fourier transform this, and so there's a corresponding commutation relation for the momentum space representation of these operators. So v hat k of tau with pi hat k prime and tau is with a 2 pi factor over here, I, and then delta of, in this case, k plus k prime. And this is just the Fourier transform of the equation above. All right? Now, for each of the solutions to the mode equation, we want to associate operators, A and A dagger, that create or annihilate those modes in the quantum mechanical picture. And so what we can do is we can write v hat k of tau as, and now our mode functions will only depend on the magnitude of k because it doesn't matter which way k is pointing. It's just that the operators themselves need to know, what state they are creating in terms of which direction the momentum is going. So we have a mode function with just the magnitude of k as a function of tau. And we have a annihilation operator for the mode k. And then this is a real scalar field. So we have a vk star and then an ak dagger. Okay. And we can now plug this into this equation. And then this gives us a normalization condition if we have the usual relation between annihilation and creation operators. Where this is equal to 2 pi cubed delta k plus k prime. Okay? And so when you impose this, this gives you a normalization condition for the mode functions, vk and vk star. And if you follow it through, it is that vk star dot minus vk, this is the other way, dot star, had it wrong in my notes, and this is equal to I. Okay, so this gives this normalization condition on the mode functions. So let's now go ahead and solve. So this puts some constraint on the coefficients associated with the solution to this second order differential equation. And in terms of those coefficients, I can write vk is equal to c plus times 1 plus I over k tau times e to the plus I k tau, and then just everything but conjugate. Okay. And so what does this normalization condition mean when I write it in terms of these coefficients? So you can shove this into Mathematica or whatever you like. And this normalization condition gives us that the magnitude of c minus squared plus minus the magnitude of c plus squared is equal to 1 over 2k. Okay? So this eliminates one of our two coefficients in terms of the other. All right? But now there's an additional degree of freedom, of course, because I haven't fixed both. I need to give some initial condition for v of k as tau goes to minus infinity, okay? And so we need some basemark state to start from that corresponds to this initial condition that we choose. So we're asking, what is the mode created by A at time t equal to 0? We have to be a little bit careful because, as you know, this is not a system that conserves energy in the usual way. This is a time-dependent system due to the fact that this mass is changing as a function of time, right? So we need to have some other benchmark for what we call here the ground state, where the ground state is the thing that is annihilated by A. And so choosing different initial conditions sort of corresponds to choosing different things that you call the ground state for this system. But when we look at this picture, let's remind ourselves that at very early times, this thing looked just like a usual simple harmonic oscillator, right? And so we can use that as a benchmark. We know what we usually use as the ground state for a simple harmonic oscillator, and we can use that to sort of orient ourselves as to how we might choose these initial conditions. Okay? So what we do is we calculate the Hamiltonian. This is one of your usual exercises in quantum field theory. You work very hard and you Fourier transform and you work out all kinds of AA dagger commutators. And at the end, it boils down to a nice expression. So you start with the usual expression for the Hamiltonian, 1/2 pi squared plus 1/2 di v squared plus 1/2 a double dot over a times v hat squared. And then you turn that crank, you work very hard, and you get an expression in terms of just the a's and the a daggers. There's probably a 2 pi cubed here that I forgot. Okay, and then some function f star of k, where these functions depend on the mode functions. All right, we're just burying the mode functions inside an ugly function that we're just writing as a nice letter. A k dagger, a minus k dagger, and then plus. So these are our new terms that we didn't see in the Hamiltonian for just the normal plane wave modes. So these are our new ingredients. And then we have the one that looks a bit more familiar, AK dagger, AK, and then plus that lovely ground state energy delta of 0, which basically corresponds to the fact that you're integrating over all of space of the ground state energy of this system. Maybe related to partly to the thing that's causing the de Sitter evolution in the first place. That is the cosmological constant. And then a function ek that is also a function of the mode functions v. Okay? And so now, now all of these things depend on time. And I'll write down one of them, the one that turns out to be most important for our part of the calculation, and that is Ek. So we know that if I were to calculate the vacuum expectation value of this Hamiltonian, this wouldn't give any contribution because these kill the vacuum state on the right. This gives no contribution because it kills the vacuum state on the left. And so we're going to be most interested in this one to help us find the state that minimizes the energy at early times. Okay? That is identifying which of the two solutions here, which combination of those two solutions gives us the minimum energy. So Ek of tau is equal to the mod of Vk dot squared plus the frequency for this guy squared, Ek squared, whoops. And now when I calculate the vacuum expectation value of this Hamiltonian, it's only going to involve the Ek, and it is that annoying integral over volume here times the integral over d3k of Ek of tau. All right? So what we can do is use this expression and extremize it over the remaining degree of freedom in these two coefficients to find the state with minimum energy. Question? So again, we define the vacuum state by that energy in the mode is approximately conserved at early times. So there's a choice here, right? Make no mistake. We have a freedom here to choose this ground state, and there's a lot of room in Hilbert space, and so we want some guidance as to pick what is a direction in Hilbert space that stands out as, I don't know about if interesting is the right word, but that is a state of merit. And it would be the ground state of the system when it is at a time where the ground state sort of makes sense to talk about. Yes, for that mode. Yep. And so this is referred to as the Bunch-Davies procedure. And so when you extremize this function here, what you find is that first, the limit as tau goes to minus infinity of Ek of tau is, rather than the difference of the c's, it is the sum over the c's squared. Okay, so now we just plug in that condition into here, and extremization is just going to lead to one or the other of these two being 0, and it turns out to be minimized at C plus equal to 0. Okay, and so now we are done in a certain sense, and maybe we can give a bit more intuition to your question when we write down the mode function after plugging in. And it's that Vk of tau is, we get rid of a phase that we don't care about. Vk of tau is 1 over the square root of 2k and 1 minus I over k tau e to the minus ikt, k tau. Okay? And so what is this mode? It's the mode that if we think back to tau goes to minus infinity. So here's the boundary, tau goes to minus infinity. These are the modes that correspond to outgoing waves from tau goes to infinity. Okay? So it makes a bit of sense if you really want to take de Sitter space all the way back to tau goes to minus infinity. However, do we really want to do that? Do we think that this procedure has been happening forever? In the context of a potential like this, this corresponds to going all the way here, and what's going on out here. We have to specify the physics of what created this inflation in the first place, and so it's not so obvious that this is the only thing you could think about trying. And so, but for our purposes, we'll make this our starting point, but just understand that there is a choice here, that this is not fixed for us. Okay, so this is the Bunch-Davies mode function. And I wrote over where I was going to write in big letters Bunch-Davies. Okay, and so, but now that we've got at this mode function, now that we have an operator that corresponds to creating a specific state at tau goes to minus infinity, now we can actually start to calculate statistics of this operator. And it's the statistics of this operator that are going to give us the amplitude and the spectrum of the fluctuations that are generated as, when we get to it, the inflaton rolling down this potential while having those fluctuations. Again, right now we're not doing the inflaton, we're just doing a massless field in de Sitter space. But we can go ahead and calculate the 0-point fluctuations. Right, so we're starting in the ground state when it's in the oscillator phase of evolution. And so what we're doing is we're just running forward and calculating the statistics given that initial condition for this operator. So the expectation value of V is just going to be 0. However, there's going to be a variance. Which is our vacuum state, V hat, tau, and we can pick anywhere, okay? 0, so this is in position space now. And, we know how to do this. We plug in the functions for the operators that we have here. This is the integral d3k, d3k prime, 2 pi cubed, 2 pi cubed. And then we have the expectation value of vk star a dagger plus vk a. Okay, and then just finishing it up over here. Vk prime, Ak prime, V star, K prime, A dagger, K prime, and 0. Okay? And I'll spare you, the manipulation that you do to get to the final expression. But it's, of course, just after doing your delta functions and all that, we get d3k over 2 pi cubed of vk of tau squared. Okay? And we can now write this as integral over d log k of k cubed over 2 pi squared vk of tau squared. And we call this quantity here the dimensionless power spectrum for V. All right. But we have V, we can plug it in, and we can calculate this power spectrum. Question? No, this is just just V squared, right? The expectation value of the operator squared. Yep, that's right. It's a real operator. Yes, it's equal to its dagger in the construction that we did that I've erased by now. Yep. Okay. And now we're almost there. This isn't quite the power spectrum for the thing we wanted, right? We wanted the power spectrum for phi before we did the field redefinition, because phi was the actual degree of freedom that we were interested in tracking. Yes? Yeah, but that's not too hard to do. P phi k tau is nothing but P nu of k tau divided by a squared. Just from the fact that V, went like phi over a. Okay, so it's just the scaling factor. All right. And we know what A is. We're in de Sitter space. This is h tau squared P nu of k tau. And this is not a hard integral to do. So P phi of k tau is finally h over 2 pi quantity squared 1 plus k tau squared. All right? So now, finally, what are we interested in? We're interested in the modes that are coming back into the horizon at around the time that inflation has ended. And so what we can do is, remember, inflation ends around tau equal to 0. So you want to take the limit of this as k tau goes to 0, which gives us a completely constant power spectrum for this mode. So there is no k dependence on the right-hand side for the power spectrum. All right? So a free scalar field has a scale, a free massless scalar field has a scale invariant power spectrum. you can repeat this process for a massive scalar field, and it is not, okay, there's more, more turning of the crank to do. You have to, follow what happens when I add the mass to the solutions and all that. But the process is exactly the same as what we just did. Before talking about what the answer is when I start adding mass terms to this scalar field, let's just get a little bit of intuition for what we expect the answer to look like. When I add a mass to a field that is living in de Sitter space, there are two quantities of merit that I want to compare to each other. There's the mass of the scalar field, and there is the Hubble radius during that de Sitter evolution. So let's get a quick idea for what we expect things to look like when I compare those two scales. So let's draw the universe, the observable universe, to an observer that's just sitting here during inflation. So the universe goes like, has a radius 1 over Hubble during this inflationary epoch. Okay? So now I put in a mass scale into the problem. Let's say that the mass is a lot less than the Hubble radius. So now there's a Compton wavelength for the particle. That is like 1 over the mass, okay? So now, if the mass is much, much less than the Hubble radius, then we expect something that's a little bit like this dimensionless power spectrum that we just got. In the limit that I take the mass to 0, we should recover the results that we got for the massless scalar field, okay? But there should be some difference, because now, imagine I produce a mode, quantum fluctuate a mode at early times. The inflation will blow that mode up, right? But at some point, the wave number for the mode has exceeded the mass, right? Or sorry, has gotten stretched out, below the mass, okay? And so there's something different that happens with that mode in comparison with the modes when the mass was vanishing. So we probably expect some deviation from the scale invariance due to the presence of that mass. Okay, so that's mass much, much less than Hubble. And of course, it's the other scenario in the case when the mass is bigger. Now, the Compton wavelength is inside. And now think about what we learned when you give a mass to, let's say, a force carrier or something like this, right? The potential falls off like the exponential of minus m over r, yeah? And so, And so what happens is the correlations for that massive particle fall off exponentially before that mode is stretched out and meets the Hubble radius, okay? It exponentially decays before the mode gets frozen. So probably in this case, we expect in the power spectrum some sort of exponential fall off. Okay, and that exponential fall off should be proportional to the mass and h. So some function of m over h that falls off. Okay. All right, so now what are the results when you go through the process? First, in general, for the mass, you get a different Bunch-Davies mode function, minus pi tau over 2. Then you get a Hankel function of the first kind of minus k tau. And then this multiplies e to the 2 nu, and I'll explain what nu is in a moment. 2 nu plus 1 times I times pi over 4. Okay, now nu is defined by the equation nu squared is the square root of 9/4 minus m over h squared. Okay? And now where does this thing come from? It comes from solving the equations of motion. And when you solve the equations of motion, this is the figure of merit that corresponds to when I get this crossover in the behavior as the mass is becoming comparable to the Hubble rate. Okay? And there's a factor of 3/2, but the intuition applies. So now you want to calculate again the variance for the fluctuations. Yes? Right, so here what I'm doing is I'm comparing the two scales in the problem. Okay, we have two scales. We have the mass and the Hubble rate, and those both are energy scales. Okay, and in terms of length scale, Hubble sets the size of the observable universe, and the mass sets the Compton wavelength of the particle. And there are two regimes, one where the particle is bigger than the observable universe, and that corresponds to the mass being less than h, and the other where the particle is smaller than the observable universe. As we learned, when you have things like masses for gauge bosons, there's exponential fall off at some point. That is, correlation functions will fall off exponentially at radii bigger than the inverse mass. To the what? Not in this case. No. The free streaming of the photons, you mean, or? Yeah, there's nothing for it to run into here, right? There's no. We haven't put in a bath of any particles in there. We're really just looking at raw quantum fluctuations of these particles in this background. Okay. And I don't know why I scribbled that out, but that's okay. So here's mass much less than Hubble. And so now let's calculate the power spectrum, or let's write down the answer that you get by just repeating that calculation over there for this new mode function. And it is that p phi, as again k tau goes to 0, is that same h over 2 pi squared, but now times k tau to the 3/2 minus nu. Okay? Now, 3/2 minus nu, if I take m to 0, is just 3/2 minus 3/2. Oh, no, nu squared is this. Sorry. Well, nu is the square root. My bad. Okay, so nu goes to 3/2 as m goes to 0. Okay, so now we see that we've picked up, for a small mass, a power law running of the spectral density. Yes? The power law has now replaced the scale invariant behavior for this guy. And so for mass much, much greater than Hubble, you indeed get an exponential fall off. And its p phi is proportional to e to the minus pi m over h. Okay? Good. Okay, so now we have these two different regimes, and before we go on to talking about how this works for the thing we were interested in at first, that is the inflaton rolling down a shallow potential, let's just see what's going on here. There's a figure of merit, there's a length scale, and that, in the case of a inflaton rolling down a potential, the characteristic length scales in the problem are going to change as phi moves down the potential. Okay? And when we reach the point at which the characteristic length scales become smaller than the Hubble distance, then something is going to drastically change in the behavior at that point. So slow roll will look a little bit like this picture, and the exit of inflation is going to correspond to when the length scales in the problem go below the radius of the universe. Okay? So that gives us a kind of basic picture of when we're going to have different types of behavior of the potential, or how different types of behavior in the potential are going to manifest in the spectral density. Okay? Manifest in the power spectrum. Why do I keep on saying spectral density? So there is a quantity called the spectral index. And the spectral index is defined as the derivative of the log of the power spectrum by d log k. Okay? And for the case of the small mass here, what we find is that this is, well, first 3/2 minus nu. That's just a thing appearing in the power law there. And then if we expand in small mass, this is just 1/3 m over h squared. Okay? And so the spectral index here is just going to vanish for the scale invariant power spectrum. Okay. Okay, so questions at this point. So next, we're going to see how to take into account the mixing between the scalar degree of freedom that we write down in the scalar Einstein equations and the metric degrees of freedom. Remember we did this counting last time? Graviton has 2 polarizations, right? So gravity by itself has only 2 degrees of freedom after I do all my gauge fixing and things like this. But now I add a 3rd degree of freedom. I add this scalar field, but because it's interacting with gravity, the actual physical degree of freedom is going to lie partly in the metric and partly in the scalar field. And so in order to do this analysis for the scalar mode that we're interested in, we have to identify what the actual physical mode is before we can proceed. Okay? So what we can do is first just write down everything that we could possibly write down without doing any gauge fixing. But we'll do it in a way that makes our life a little bit easier. So to identify the scalar mode, let's first start off with the most general metric that we can write down. Okay. And so what does this metric look like? It's just n squared, and then sort of the vector hij dotted to ni, hij, nj, okay. And then over here, we just have 3 by 3 block hij, okay? And we can count the naive degrees of freedom in this metric. And so we get 1 plus 3. It's symmetric, so we get only 3 degrees of freedom there, plus a 3 by 3 symmetric matrix, which gives us 6. And so we have a total of 10 naive degrees of freedom. Okay. Now remember when you, so n is for naive, okay? Now remember when you do QED, there is an A0 that doesn't have any dynamics. When I write out the action for f mu nu squared and I look at the A0, that field doesn't have any time derivatives on it. It's not a dynamical degree of freedom. That's the same here, but here it's all of the n's that do not have any time derivatives on them. And so n and ni are not dynamical. And so in that case, I am down to 6 degrees of freedom. Okay. Okay. If they are not dynamical, then we can just impose their equation of motion. We write out the full action that involves these n's and ni's and the rest of the degrees of freedom, and we can integrate them out. So we get constraint equations from the n's. Now if I add the scalar, we now have phi and hij are our remaining degrees of freedom so far, which gives us 7, again naive degrees of freedom. Now, finally, let's write hij in terms of a piece where we've pulled out the trace of hij. Yeah?
This is just a generic metric. Are we working in civil background?
Right now, this is just a generic metric. If you like, n squared carries the time dependence in it. So I'm just starting from scratch. We have a general coupled scalar field coupled to gravity, and just working out, what do we get in the final action after solving for all of the fluctuations. So phi has a background in this case, right? Phi is phi plus delta phi. And n has a overall a squared in it, okay? Or sorry, hij has an a squared in it. So let's pull out a scalar degree of freedom out of the metric and define an h twiddle that is just h with the trace taken out. So now we do something like we did for electromagnetism. We impose a gauge, right? We make some gauge choice. For, let's say, h twiddle, it might be something like Coulomb gauge, where I take di, h twiddle ij, and I set that equal to 0. Okay? So when I do this, this is, okay, so this originally had 5 degrees of freedom. Now I subtract 3 constraints, and I'm left with the 2 graviton polarizations. Okay? So this had 5. Now, after imposing this, I'm left with 2 in the tensor fluctuation there. And I impose one more condition that relates phi to this trace. Okay? So we could do something like maybe set delta phi completely equal to 0. Okay? That is, we have phi is equal to phi bar of t plus delta phi. And what we do is we just completely remove the fluctuations here, giving only 1 more degree of freedom. Okay, so now we're down to 3 degrees of freedom, but we don't know what the action is until we impose the constraint equations. And okay, so this is a messy business. You have, there we go. You have some function you can define in terms of these n's, this k. You write down the original action that you start with that has everything in it here, and then you write out the equations of motion for the n's. And once you impose some gauge condition, it is the equation of motion for the n's that tells you what the expressions are for these pieces in the metric that then finally give you the resulting action for only the physical degrees of freedom. Now, it's not going to make us feel any better to go through the actual solution to these yucky equations. So once you go through this procedure, what you get out is an action that only has the physical propagating degrees of freedom in it, with all of the gauge freedom removed. And if you cut to the chase, so we start from the simple thing that has many fictitious degrees of freedom in it, We'll set m Planck squared to 1 just for convenience for writing this down for the moment. So we start with this. And once we impose all of the gauge constraints, and I'll take the yucky equations away just so we don't have to look at them anymore. Just turn the crank, you get the actual action in terms of only the physical modes. And this will just be, OK, an action that has only the physical propagating degrees of freedom in it. Yep. Yes. Sorry, I can't quite hear you super well. Yep. Yeah, so we're writing down just the action. We're doing the usual Euler-Lagrange equations of motion for this action for these degrees of freedom. So you can think about this procedure in terms of a foliation like this, where each of these k's that is written up there is the extrinsic curvature of those foliations that you add. I didn't want to go into the details of this because it would eat up too much time. I just wanted to give the basic picture of how you go from an initial action that has way more than the expected number of physical degrees of freedom, and what the procedure is to boil it down to only the physical propagating degrees of freedom, which we know must consist of 2 graviton polarizations and only a single scalar field. Yeah, there can still be a background. There's nothing preventing us from having the de Sitter background on this. Okay? But here, the de Sitter background will be driven by solving the equations of motion once I have everything in terms of only the physical degrees of freedom. Okay, so I don't want to spend too much time worrying about the complicated details. This is more just to show you the procedure and prescription for how you get to what we want, which is an action only for the scalar mode. If we have time, and I hope we do, we'll talk about the tensor mode as well. But for now, let's focus on just the scalar mode. OK, and so quickly, the answer looks like Hij is equal to, at linearized order, the background a squared times 1 plus 2 zeta times delta ij. N is some alpha of t and x, a fluctuation, and then the ni are written as di of some beta, and these alpha and beta can be written down after solving those constraint equations. You solve those constraint equations, plugging in this ansatz, and you relate everything. And now we're only focusing on the scalar mode. So these constraint equations will eliminate 1, 2, 3, 4 guys, right? So I get rid of the ni's, and we get rid of all of the alpha and the beta in terms of just the zeta and phi. But if we take delta phi equal to 0, let's say, which would correspond to picking a gauge where you, say, start off with constant phi surfaces, and you then go to a gauge, just like we were talking about before when we fixed the adiabatic fluctuations, where it looks like this in terms of phi. But all of these perturbations, when you do this gauge fixing, you push all of that single degree of freedom into the metric. And so what do we get after doing that? Rather remarkably, it's a very simple action for just the scalar. It is just 1/2 integral d4x root g, and then, let's get rid of the root g, let's plug in the background. A cubed, that epsilon parameter that was minus h prime over h squared, and the zeta. Okay, so the end result after turning this long, sort of yucky crank is a very simple action, quadratic in zeta, that has time dependence in its equation, right? In its action, we have a normalization condition that depends on time, and before we do what we did before, which was rescale and get things canonical, we can write this as, well, we can write down the equation of motion. Just to see one thing in passing, the other slow roll parameter shows up in the equation as well from the time derivative on the epsilon. H zeta k prime, and then plus k over a squared zeta k. And what happens when a mode is stretched super horizon is that this k over a goes to 0 rapidly, and we're left with an equation where there is clearly a constant solution, right? We have primes in 2, right? So this means that when a mode goes super Hubble, there is a constant solution, which means the mode is frozen. There's also a growing solution, but we know that that's not a physical thing. This mode can't grow without bound. So there's a constant solution which tells us that the mode freezes once we're outside the horizon. That's why this zeta, if we go way back, was a convenient way to parameterize the perturbations, because that is the description of the mode that does not evolve once it's outside the de Sitter horizon. Okay? So then we do what we did for the phi's and v's. We rescale so that we can get a simple harmonic oscillator like equation. And it is just this following rescaling, a cubed epsilon and zeta. And if we define this as z zeta, it's really just like the equation we had before for the massless scalar, but now with z derivatives instead of a derivatives. And we have v double dot, particular mode number k, plus k squared minus z double dot over z vk is equal to 0. Okay? So now these a double dot over a, z double dot over z always depend on tau in the simple way 1 over tau squared, but with different things in the numerator, right? There was a 2 over tau squared if this was a. In this case, because we're factoring in the Hubble evolution during inflation, so Hubble is not going to remain constant anymore. We're not in a pure de Sitter background. We're in the background dictated by the classical solution to the inflaton equations of motion. And so z double dot over z is some index nu squared minus a quarter over tau squared, which is related to the slow roll parameters. Or just the parameters governing the movement of the inflaton down its potential. Okay? So now, this is very much like the massive field in de Sitter that we were studying before, right? Where we had a different thing appearing here on the right, but nevertheless, this thing shows up in a similar way when we calculate the power spectrum. The Bunch-Davies function is, again, the Hankel function, just like it was for the massive field in de Sitter when the mass was small. And if we take the limit as kappa tau goes to 0 again, once you impose the same Bunch-Davies initial condition, this is some numerical factors square root of k times minus k tau to the negative nu plus 1/2, where nu is this function of the slow roll parameters. Okay? In the same way as before, we calculate the variation due to the quantum fluctuations of these modes. And we get, for sort of our final answer for the power spectrum for the physical mode zeta, this is 1 over 16 pi squared. H squared now depends on tau. We have epsilon, which is h prime over h squared, depends on tau. Okay. Now these factors have time dependence that turns out to cancel this time dependence. And so we can write this in a final form with some value of tau corresponding to the end of inflation, sort of like which gives us a reference scale. Tau star goes like 1 over k star. And so we can write this expression in terms of k star, which when we work it out, is 8 pi squared 1 over the value of epsilon near the end of inflation, h star squared over m Planck squared, and then k over k star. And now we have a power in it due to this non-trivial value of nu to epsilon star minus eta star. What's that? Yeah, so K star is just really it's any length scale that you might choose as a reference, but you might as well choose a length scale corresponding to either the beginning of inflation or the end of inflation. So you might say K star corresponds to the mode that just barely goes outside the Hubble horizon by the end of inflation, something like this. Yes, yes, yes. So we are near the end of inflation. Tau is close to 0. Yep. And so if K star is 1 over tau star, then tau star would correspond to the time at which I exit inflation. So now you can calculate the spectral tilt. Just d log p by d log k. And it's 2 epsilon star minus eta star. And so we have a prediction from this coupled scalar gravity system that during slow roll, the perturbations that are created, right, the quantum fluctuations that go outside the horizon and then come back in at later times are going to have an approximately scale invariant power spectrum where the deviations from scale invariance are giving you information about the parameters of the potential that was driving inflation. So there's initial conditions zeta that grew into the fluctuations in the CMB and to fluctuations in the matter density later are impacted by these initial conditions, which in turn are determined by the parameters associated with the inflationary physics. So when you measure the spectral tilt in the CMB, you are measuring, in part, there might be other contributions from other physics between when inflation ends and when recombination happens, but we know that physics, or if we add some new physics to the scenario, we know how to calculate its effects, right? And so this scale non-invariance, so scale invariance breaking, imprints itself on late time observables. Okay. Okay, good. So now, remember, we can think about when we compare different models, we want to have some model of reference. You might say that our model of reference, because what we see is very close to this, so our reference probability distribution for zeta can be considered as completely Gaussian and completely scale invariant. That leads to one set of predictions for what we see. And now we have alternative hypotheses to compare to sort of that sort of reference toy model, which we know will not encapsulate all the physics, but that we can still use as sort of a model of merit for comparing what we observe to some reference model. And so what we see is that slow roll inflation gives us a near constant spectrum, but with a spectral tilt encoding the physics of inflation. Okay, so we have a little bit more time, and I think just enough time to do gravitational waves. Are there questions about what we just wrapped up? Yeah. Okay, so you're asking the wrong person. I know, from sitting in talks that we're getting to a part in 10 to the 2, or maybe even better, on a lot of the parameters of inflation and other models, but I don't know exactly how much wiggle room I have in the spectral tilt. I know it's like 0.97 or something like this, but I don't know exactly what the error bars are. But we are getting. I can say this, I know we are getting to a point where we can rule out classes of inflationary models. So there are interesting models that are no longer interesting because they've been killed by data. And like we were talking about when we were talking about n-effective, we're going to make big improvements, hopefully soon, when other new CMB experiments come online. Other questions? I thought there was another one. No? Okay, so what about gravitational waves? So there was the Hij twiddle that we left out, right? We knew this guy was there in the metric. We knew that we could impose a gauge where only the graviton polarizations were left. And those two polarizations are the sort of two squeezing modes. Oops, wrong way. Okay, so we have these two polarizations. And if there were primordial gravitational waves, the way that they stretch and squeeze spacetime can imprint itself on the CMB in terms of what we call the tensor modes, or the B modes, a certain class of polarization modes. And so what we'd like to know is how big is the effect for a given inflationary model. So when we do the gauge fixing and all that mess, we can boil things down to only the physical degrees of freedom, the two polarizations of the massless graviton. And when we write down that action, it is m Planck squared over 8 integral d4x of now just a squared h twiddle ij dot squared minus d hij twiddle squared, let's say, I don't know, a. And so again, the action is a simple quadratic one, and we can write now the matrix H as, for example, for a mode whose momentum is in, say, the 3 direction, there will be a, let's skip to the V writing, V minus, oh no, this is plus, and then V minus, V minus. So here is a mode characterizing the two polarizations of a graviton moving in the 3 direction. And we can write this as m Planck A over 2 Hij twiddle is 1 over root 2 times this matrix, which now puts this in terms of the V's. And we finally have an action S that is just the sum over those two polarizations. Okay, the vertical squeezing and then the diagonal squeezing. And then everything is canonically normalized. Let's summing over lambda, let's say. V lambda dot squared minus d v lambda squared plus a double dot over a v lambda squared. Okay? And so we write down the equation of motion for the v's. And so now we're repeating the same thing over and over again. What we're doing is we're getting everything in terms of the scalar degrees of freedom. We are quantizing those modes. We're imposing the Bunch-Davies condition, and then calculating the variance in the expectation value of the operator squared corresponding to these modes. And when you get through this, you find an expression for the power spectrum for the gravitational waves. pH twiddle of k, that is 2 over pi squared, and again, going to some characteristic length scale at which we evaluate Hubble, m Planck squared, k over k star, to, in this case, minus 2 epsilon star. Okay, so it has a spectral index that depends on one of the slow roll parameters, but which depends differently on the slow roll parameters than the spectral index for the scalars. And if you look at the coefficient of the power spectrum here and the power spectrum here, you see that there are differences in the amplitude for the power as well. Okay? So we can now do things like, say, I measure the power spectrum in the scalar modes, and I want to ask for a given model of inflation, once I have the power in the scalar modes, what do I expect the power in the tensor modes to be for those parameters of the theory? So this might allow us, for example, to disambiguate between models with different Hubble rates during inflation. So you can go ahead and do this. So now we're looking at the power in the tensor modes versus the power in the scalar modes. And this is going to, when you work out all the factors, I think I left out, oh no, I didn't, it's over there. Okay, good. So when we calculate this ratio, you get 16 epsilon star k over k star raised to the power eta star minus 4 epsilon star. Okay? So now this means that in this ratio, we have this slow roll parameter showing up. Okay? And that slow roll parameter dictates the overall amplitude of the ratio of these guys. And we call that thing out in front in this ratio the scalar to tensor ratio. Okay, and so now you can go ahead and look for the effect of these tensor modes in the polarization of the CMB, and you can put constraints on different models of inflation. So that's what we're looking at right here. So in the panel on the left, you have the spectral index going along the horizontal axis, and the tensor to scalar ratio along the vertical axis. There is a couple of lines going through this, one of which corresponds to the m squared phi squared model that we looked at briefly in the last lecture. And what we see is that that m squared phi squared model is actually ruled out by the data now. So you've taken the simplest model of inflation, which we knew didn't look quite good because we had to have these trans-Planckian field excursions in it. But that kind of is ruled out by the data now. So, and the right is just, I think, the likelihood so that you can sort of parse out exactly where the best fit contours are on the left-hand side. So that's like the likelihood ratio of the different points in this plot as a function of only the tensor modes. So I think they're just trying to say here that the data slightly prefers something above 0, but it's not serious enough to really say that there's a definite non-zero tensor to scalar ratio yet. Okay, and so now we'll just have to be wrapping it up here since we're kind of out of time. But this is actually really remarkable if you think about what it is that we've been doing and what its implications are if we were to measure a non-zero tensor to scalar ratio. We calculated this power spectrum relying on the fact that gravity is quantum mechanical, right? So by observing a non-zero tensor to scalar ratio, you are confirming that along with all of the other particles we see, that quantum mechanics also applies to fluctuations of the graviton. And that is really cool if you think about it, that by looking at the sky, we can decide on one of these more fundamental questions whether or not we're supposed to quantize gravity the same way as everything else. I mean, yeah, probably we have to. Gravity sort of mixes with modes and things like that, but it's still really nice to get that kind of a final confirmation from data. And so it's really exciting to see what comes up from these future experiments. I encourage you all to go ahead and work through a little bit more of Baumann's notes or anything else if you want to learn more about non-Gaussianity and how other physics imprints itself on those non-Gaussianities. But I can tell you that the procedure is very much what we just did here, only you have to do more cranking of the quantum mechanics, right? We have to start doing Feynman diagrams involving the new physics, things like decays of heavy particles, or maybe self-interactions of the inflaton. And they will show up in a way of parametrizing those non-Gaussianities that we call the shape function. And so here are just two different pictures that disambiguate between two different classes of new physics scenarios on top of standard inflation, with the one on the right looking like what happens when you have new self-interactions of the inflaton, and the one on the left being what happens if you have a bunch of new massive particles in addition to the inflaton whose masses are within that regime where they can have an effect, where their masses are smaller than the Hubble scale during inflation. So there are other things you can do with the CMB that can get even deeper into what the physics is going on at these very early times. All right, that's all I've got for you today, and I guess for this week. And I hope you enjoyed your first week at the school. It's been a pleasure for me to give these lectures. I remember being told at some point that you've really succeeded if you reach at least one person in the room, and that one person in the room learns something. I know I've succeeded this time because I learned a lot this week. And so I hope at least I got somewhat above that very, very low bar, and that some of you have gained from what we've done over this time. All right, thank you. So other questions?
Thank you, Jay. And of course, I'm pretty sure you succeeded way on this bar because you have at least 2 people. You know,
Well, thank you.
That learned a lot. So it's a factor of 2. So more questions for Jay. Been a lot of questions.
What we did for the first 2 lectures was how we progressed the initial condition.
Right.
Tau equals positive epsilon up until some class scattering.
Yep, that's right.
What we're talking about is correlation functions all from like rho gamma, the photon path. That's the initial. Then you develop that over time until recombination. But what we've done here is take the inflaton correlations from tau minus infinity or whatever to minus epsilon.
That's right.
So it's 2 questions. First of all is what happens is like between minus epsilon and epsilon, you said like the heating, which is completely unspecified. How do we know how it affects the correlation functions? That's question number 1. Question number 2, even if we knew, it's not the same correlations. This is correlation of the inflaton, these are correlations of the photon. So how do we
What's nice is that we expect at least all of this to map on to a set of different scales, right? So there's sort of the end of inflation, and that corresponds to one scale on the sky, yes. And then there are when inflation ends, then there's a scale at which inflation ends, like the value of Hubble then, and maybe the mass of the inflaton. And those scales should also imprint themselves on the physics. So I guess if we wanted to really complete the sort of sketch of maybe what we've done this week, you're right that we have left a hole in that. This is good, by the way. You want to have places where you can do something and you can write papers about that can hopefully later be either ruled out or confirmed by observation. This is an industry where there are things to do. So we have sort of the far initial conditions that are set by inflation. And before that, okay, we impose this Bunch-Davies condition to set the initial conditions before there, but there's really question marks, as I tried to say at that point. Inflation now seeds the initial perturbations. There's the end of inflation, and then some unspecified physics of reheating. And at that point, we then go through the evolution where we know a lot of the physics, but maybe things have to happen like baryogenesis and leptogenesis. So other problems get fixed. And then we start to reach road marks where we know the physics pretty well, like the electroweak phase transition, modulo maybe a bit of model building because we don't know everything that's happening at the electroweak sector. We have the QCD crossover, okay. We have Big Bang nucleosynthesis. Maybe there's dark matter freeze out at some point. If it's axions, it's actually a different story. There, I want actually the axion to be in some particular point before reheating happens, so we don't create too large of an N effective like we were looking at last week. Okay, I don't know where to put that since I already put dark matter, but you get the idea. And then I have that surface of last scattering, okay? And then we just evolve forward, using the elements that are present in the universe governing the evolution of the perturbations that were initially seeded by zeta. And so, yeah, there's a lot of stuff in between there that can imprint itself on cosmological observables, maybe some of them on the CMB, maybe some of them on other observables that you might look at. But this is kind of the basic picture. Yes, this will affect things. Yes, this will affect things. And so it's up to you to disambiguate between the effects of this stuff that you put in and the effects of what's happening during inflation. So at the end of the day, we hopefully want to put answers for what's happening to all these things and get a model that doesn't have more parameters than observables, ideally, and get at the way the universe works, right?
But you do have to assume something, right? You did the cross like you just showed before, and that's for
Yeah, so we assumed that whatever happened here, it didn't screw everything else up. I don't see, because there's a separation of scales in the problem, this end of inflation corresponds to one scale, and so the temperature induced by reheating is some other scale, and because of this separation of scales, we don't expect this to have too much effect on what these zetas were here, right? And so if you really violate that separation of scales in some way, and you find a consistent model to do that, maybe you can find something that somehow confuses you about what these zetas were, but you have to specify what that is. I look like I didn't answer your question. Maybe we can chat about it afterwards. Yeah.
I think the point is that maybe once you freeze all the perturbations as they leave the horizon during inflation, then when they come back, this sliver of reheating is not going to affect the delta K corresponding to this is not going to affect the spectrum of perturbations that you created in all the spectrum of Ks once they left and they froze. So the idea is that you assume that reheating happens in the
and so maybe we could actually even answer the question more directly. The scale of reheating is a very, very high scale. And so when I'm looking at the CMB, we're looking at mostly pretty long wavelength stuff. We only went out to L equals a 5,000 or something like, I forget where we went out to L in the plot. But the physics that's going on here is very, very short distance scales that would be way off on the right, in that multipole expansion. We don't expect that very short distance physics has an effect on what we can see so far of the CMB. And in fact, the CMB doesn't give us very information at short scales because of that damping, right? There, we're only carrying the information, about oscillations in the photon baryon fluid, but there was the phenomenon of cutoff that led us not to be able to get that much information about those. What we can do, actually, and then maybe this is a nice, gravity waves, they sail through stuff, right? They don't get, much affected by any of the intervening things here. And so when these come through, they really don't give much of a darn about what's going on in between. They do depend on things like the evolution of the scale factor afterwards, because gravity does feel the background geometry. And so I'm going off a little bit, but if you, let's say imagine I start with a scale invariant spectrum of the tensor modes, and I'm able to construct, the best observatory that really gets all of the tensor modes out of this and really is able to measure short wavelength gravity waves and long wavelength gravity waves, looking at pulsar timing. Okay, yeah, you imagine like a perfect world where we can get the full spectrum of these. As a function of wave number, there's a power spectrum for these H tildes, and let's say this is the mode number corresponding to that epoch of reheating, okay? So this is K that corresponds to the temperature of reheating. There's some physics going on at this point where the scale factor evolution has changed dramatically, and so what I expect is this spectrum of gravitational waves to change its character both before and after this epoch that changed the evolution of the scale factor. So let's say I have, this would look like, well, I don't know. Let's just leave it like this, okay? So you can get steps in the power spectrum of gravity waves. When I start off with a constant one, the evolution of the universe will create a feature in the spectrum that was not there in the initial conditions, but has the imprint of the physics at later times, okay? So things like phase transitions imprint themselves on the gravity wave spectrum. So if I start off with something scale invariant, say a Peccei-Quinn breaking that happens in the intervening time will imprint itself on the spectrum. And that's something you can't get at with the CMB because you have no power at short wavelength.
More questions, comments? Okay, so let's thank Jay very much for his great lecture. I want to try to thank you because I cannot thank you enough. Before
it was
you
a pleasure.
guys go, announcements, quick. So first quick announcement.